part on the chapter, we are going to discuss cross-validation techniques. If you remember, we conducted goodness of fit models or measures to assess the performance of the model using sample dataset. Do you remember when you use standard error, SE, adjusted R squared or R squared? We use these measures to assess the performance of the model. But the problem that these measures cannot be used to gauge how well an estimated model will predict in unseen data. So including more variables that does not have an economic justification would help to improve the model very well, but it would perform poorly on the unseen data and it would have poor predictive power. So that's why we need to think about using cross-validation techniques. Cross-validation is to assess how the chosen model performs on different subsets of data, especially on the unseen data. Sometimes we are going to have a problem of the overfitting. What is overfitting? Overfitting occurs when the regression model is made overly complex to fit the quirks of the given sample data. By making the model conform too closely to the sample data, its predictive power is compromised. To assess the predictive power of a model is to test it on a data that not used in the estimation. So that's why we go for the cross-validation techniques. The idea of the cross-validation technique is partition the sample into two sets, training sets and validation set. In the training set, the goal of the training set is to estimate the model, and the goal of the validation set is to assess how well the estimated model predicts with unseen data. So we train the model using a set of the first partition of the data. When we build the model, we do prediction on the unseen data and we see how well the model does with the unseen data. In this chapter, we are going to discuss two methods of the cross-validation techniques. The first one, we call it hold-out cross-validation method. What is the process that we are going to do? We are going to partition the sample data into two independent, mutually exclusive parts, two separated disjoint parts. The first part is going to call it training set. The second one, we're going to call it validation set. And we are going to use the training set to estimate the competing models, model 1 or 2 or 3 or all of them. Then we are going to use estimates from training set to predict the response variable in the validation set. So we're going to use the model that we have built. The estimates, we're talking about the models here. The estimates, they are the B's, right? So we are going to use the model that we have built using the training to predict the response variable in the validation set. After that, we are going to find something called RSE, which is the root square mean error, which is basically nothing but the difference between the predicted value and the observed values. So it's the sum of the difference squared. So and it's the mean. So we divide by the total. The n we take square root. So this is the formula is the difference between predicted values and the observed. So the goal is to minimize this. So we are expecting this to be the minimum, right? So that's why the lowest or smallest RMSE is going to be our preferred model. So the goal is what? Is having models that do well for both training and validation data. Other than this will indicate that we have an overfitting problem. In general, we will have no issues with number of observations. We're going to have a big number of or large number of observations to have an effective estimation and assessment. The second technique is using k-fold cross-validation method. Why do we need to consider the second technique? Because the first one sometimes is not doing well. I mean, the first one depends on the way that we partitions the data. So the model will be created based on the way that you are partitioning the data into two sets. So that's why this is not enough. Maybe if I partition the data in a way, okay, randomly, if you partition U in a different way, randomly, maybe we're going to get different models and different prediction powers. So in this case, we use the k-fold cross-validation techniques. The k-fold cross-validation technique, it depends. K means what? You divide your data into k-folds, k parts, 3, 4, 5, 6, 7, it depends. If you divide, for example, your data into 4 folds or 4 partitions, what you do, you take the first three, and you put them in the training data, and you leave the fourth one for the validation data. You build your model using the first 3, then you test your data using the validation data. You use the validation data to do the prediction. Next, what you do, you use the second and the third and the fourth part. You put them together. They create the training set. You build the model. Then you use the first set to do a prediction, which is the validation set. Third time, you pick the first and the third and the fourth set. You put them together. You create a training set. Then you repeat this again. So basically, you're going to create you're going to construct 4 different models. And RMSE will be calculated in each cases, and the average of RMSE will be given back to you. So the average of the performance measures is used to find the preferred model. If K is equal to the sample size, the resulting method is a new one. We call it leave one out cross-validation method, when in fact you leave just one observation for the validation set. And as I said, you will have an RMSE value from each of the 4 validation folds. I give example about 4 here, so that's why K is 4. The reported RMSE for the K-fold cross-validation or the 4-fold cross-validation is the average of these 4 values. Averaging the RMSE values from each fold give you a more robust estimate of the model's performance than relying on a simple train test split, which is as we said in the first technique. So if possible, we recommend to use K-fold cross-validation method when you use cross-validation techniques to build models.